All right. So again, apologies for needing to leave class early, but this is essentially our kind of fill-in part. And what we need to do now is really get caught up at least a little bit on DNA replication in prokaryotes, right? So the whole deal about this is that prokaryotes are, generally speaking, not always, but generally speaking, simpler than eukaryotes, right? So if you want to learn a principle or process, then starting with prokaryotes kind of makes sense, right? Because it's a little bit less complex. Same argument really for using simple eukaryotes like nematodes for research, right? They're a little bit more tractable. Okay, so we do get that in the beard. And okay, so just to recap, essentially we're dealing with a process that goes through several phases, right? And really initiation and unwinding kind of go together, as you'll see in a second. Elongation is fairly straightforward. It's really DNA polymerase doing its job. And then termination isn't just the ending of DNA replication, but it's all the other stuff that has to be done so that you have a complete genome, right? Without any gaps in it, without any breaks in the backbone, stuff like that. So as I mentioned earlier, both prokaryotes and eukaryotes have what are called origins of replication or replication origins. E. coli or bacteria only have one. It's called the ORI-C. So typically all genes in bacteria have, three lowercase letters, whatever that might be. ORI stands for origin. Sorry, cat fur falling in front of my eyes. And then a capital letter after that. So that's kind of where that's coming from. And so really the deal here is that you have proteins coming in that will recognize that replication origin, and their job is to bend the DNA so it pops open, right? And this short stretch downstream of the ORI-C, that has a very high AT content, right? And so the bonds holding together those two strands well, I mean, the bonds aren't weaker, right? They're just hydrogen bonds. It's just that there are fewer of them, right? So the overall kind of force holding those two strands together is lower than it might be elsewhere on the genome. And so when these initiator proteins bind, what they do is they wrap the DNA round, and in process, I always kind of struggle to do this. It's kind of like the DNA is like that, and then they bend it, and it kind of pops that bit of DNA open, right? To create, as you remember from before, one of the requirements of DNA replication, which is single-stranded DNA, right? And so now this little bubble in the DNA, this can serve as the basis for DNA replication, right? First things first, right? That DNA will want to stick back together, right? It's being held open really by the conformational change induced by these initiator proteins. As soon as they go away, bonk, it will just pop back together again, right? And so one of the first things that binds to that single strand of DNA is rather unimaginatively named single strand binding proteins, right? And their job is not to take part in DNA replication. It's simply to prevent that DNA from closing again, right? These will get punted off pretty quickly as soon as DNA polymerase comes through. You also need a protein to actively unwind the DNA. So this initial conformational bubble, right, is enough to allow these proteins to enter that space, right, to access that single-stranded DNA. But you then need to expand it, right? You need to make it bigger, right? And that's the job of helicase, right? And a helicase is really an unwinder, right? Its job is to conformationally change the two strands of DNA so that they are forced apart, right? It's really like a zipper, right? The zipper on a zip. It kind of just goes down the middle of the DNA and it just kind of pushes it like a plow almost, right? Kind of through, pushing those two strands apart and allowing these single-stranded binding proteins come in and stop it from going back together again. Now, and it's funny actually, because a lot of these processes are like, well, that's great, you know, that's a really cool thing. And you then go, but it causes problems, right? So in prokaryotes, this is a circular piece of DNA, right? Kind of goes all the way around off the page, kind of, and underneath. And so if you unwind it's actually like a garden hose in some ways. I always struggle with those things, particularly cheap ones, right? If you unwind it to get rid of a kink somewhere, right, which would be like here, you tend to induce a kink somewhere else, right? It's really difficult. Like once a garden hose is kinked, it's like, throw away kind of deal, right? And in DNA, you can't have that, right? Because as these helicases spread out, they're going to be unwinding DNA, but then as a result, you get the kind of the opposite reaction in the rest of the genome. So the rest of the DNA winds more tightly. And if that's allowed to continue, it will end up with a complete, like, kind of super coiled, like jumbled mess of highly coiled DNA ahead of that replication fork, and you won't be able to get to it, right? You physically cannot unwind it any further, right? And so what we need to do is use a topoisomerase, and topo is, where was it? Like it's, I'm trying to remember, it's shape, and then isomer is the opposite, right? And so essentially what topoisomerases do, of which DNA gyrase is a bacterial one of that family, right? We will remember, where is it? Up here, right? This is eukaryotes, it's called topoisomerase. In bacteria, it's called DNA gyrase, but it's essentially, they're the same thing. What they do is essentially you have your two strands here, right? And they're getting ever wound up, right? So it's kind of twisting up. What DNA gyrase does is it either induces a single or a double-stranded break. In bacteria, typically it's a single one. And it basically breaks it, and it just allows the DNA to go, whew, right? And relax, right? It's almost like you got that annoyingly coiled garden hose and you just cut it, let it unswivel, and then stick it back together again. Right? And that's what DNA gyrase and topoisomerases do. The actual mechanism behind that varies from one to the other, right? Some of them just break one strand, the others break both. But as soon as that break has occurred, right, and you've got that break here and it goes kind of basically swivels round, right? So you relieve that coiling, that tension. It'll then stick those backbones back together again. And it does this continuously, all the way down until essentially the whole process is finished, right? It doesn't stop, and it's always just ahead of the helicase. So it's able to remove those supercoils ahead of the replication fork. It's kind of like if you put a pencil in a piece of rope and you try and separate the strands, right? If you don't have the rope attached to anything, it will spin essentially in the opposite direction to the helix of the strands. Try it sometime. It's kind of fun. Obviously not with a rope that you want, like one that's holding up a bridge or something like that. Okay. So then the next thing we need to do, the next problem to overcome, is the fact that DNA polymerase cannot add a nucleotide without a 3' OH to add it to, right? And so if you look at this single strand here, right, DNA polymerase is going to come in and it's going to bind around here somewhere, and it's going to scooch down there. There's nothing else there. There are no other nucleotides because it's single-stranded DNA, right? That's the whole point. But if DNA polymerase can't add to something that's not there, how do we solve that problem, right? The way we do that is we actually use an RNA polymerase. That's kind of the funky thing, called primase. And what it does is it synthesizes a short stretch of RNA complementary to the template strand, right? And actually, I mean, essentially, it's the same as what RNA polymerase does in transcription to make mRNA or other RNAs, right? Difference being is it does it very short. It's usually like 15, 20 nucleotides long at most, and it stays stuck, right? It doesn't kind of end up flapping off in the breeze like mRNAs do, right? But the purpose for that is that now at the bottom of that last RNA sugar, you have a 3' OH, just like this one. And so now DNA polymerase can come in and add a new nucleotide, catalyze that phosphodiester bond, move along, another nucleotide comes in, and so on and so forth, right? So really, all that primer does, like the primer in a bullet, essentially, right, is it starts, or primer in a, an epoxy, right, to harden it. All it does is it starts the reaction. It's all right, loves, it's all right. I'm just recording a lecture. Sorry, teenagers. All it does is provide that 3' OH. Once it's done that, it's largely not needed anymore. But every time you need to start DNA replication, you have to create that 3' OH. You need to synthesize a new primer. So for the lead-in strand, easy peasy, right? All you have to do is make one single primer, you can see up here, and off at the races you go, right? Our DNA polymerase, chugga, 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 goes along, following or trying to catch up with the replication fork up here, right? However, for the lagging strand, you're synthesizing it backwards, essentially, right? You're synthesizing in that direction, but you're going backwards. So you will always hit the DNA that you've already synthesized, right? And then you need to start again, synthesize a new primer, do a little bit, hit what you've already done, like the previous primer essentially, and so on and so forth, right? So that's why you have all these little chunks, and every single time you make one of these little fragments, you need a primer. Okay, and so this is why we call this the lagging strand, right? Synthesis occurs at the same rate as the leading strand, right? The whole caboodle moves together behind the replication fork, right? For both strands. But for the lagging strand, every few hundred bases in eukaryotes, or every few thousand or so in prokaryotes, you have a primer. It's RNA. Not only is this RNA, but this is a single chunk of DNA and RNA. So if you were to leave it as this, A, you would have RNA in your genome, which wouldn't be good. And B, if you were to try and copy this, you'd only be able to copy it in little chunks. How would you transcribe this if this gap happened to be in the middle of a gene, right? You couldn't. As soon as you split that DNA open, that little piece will basically fall off, right? So for every single one of these fragments, and also for the start of the leading strand too, we have to fix those gaps, right? So in E. coli, there's 5 DNA polymerases in total. There are more in eukaryotes, obviously, and they do slightly different things in different ways. But essentially, the middle one, number 3, its job is to synthesize the bulk of the DNA. That's its job. It's pretty good at processing. It's reasonably fast, relatively accurate, but it can't remove RNA primers. And so the job of number 1 is to remove that primer and fill in the gap. The other ones tend to be involved in DNA repair, of different sorts. And so the job of DNA polymerase 1 essentially is to remove the RNA primer 1. That's going to leave you a single-stranded DNA, which is bad, right? Synthesize essentially fill in the gap, right? So add nucleotides so it's no longer single-stranded DNA. And then you have a final job, which is to stitch together the backbone, right? So even once you fill in those gaps left by the RNA primers, you will still have a gap or a nick between the last sugar and the first of the previous segment and the first phosphate of the next one. You need to create a phosphodiester bond to join those together. Otherwise, when you denature that DNA or you separate it for either replication or transcription, that chunk will fall off, right? It's not good. Don't want that to happen. That'd be disastrous, actually. So this is the process by which that happens. So essentially, DNA polymerase comes in, right? DNA polymerase 3 is, off doing its like glory day stuff, right? Doing most of the DNA synthesis. DNA polymerase 1 comes in and essentially it both removes the RNA, right? So it chews them up, right? Kind of like Pac-Man style, comes along, breaks those phosphodiester bonds and spits out the RNA nucleotides. And as it does so, it adds DNA nucleotides in, one at a time, right? So it's kind of like shoveling at the front and like putting down at the back as it kind of walks along the track, basically. And that basically fills in that gap that was originally left by the RNA primer. Now, the last thing that needs doing is we have to join those two bases together, those two nucleotides, with a phosphodiester bond. And so the enzyme that does that is called DNA ligase, right? It uses ATP, to provide the energy to create that phosphodiester bond, right? Between the 3' OH, make sure this is that way, between the 3' OH on this nucleotide and the 5' phosphate on this one. Once that is done, it's finished, right? And so essentially, in most cases, DNA replication finishes when the two replication forks meet. Although there are other cases where termination proteins come in and actively stop the process. Okay, so I think I'm going to call it a day there. I think that's probably a good amount of time, cover those basics. What we're going to do on Tuesday is talk a little bit about DNA error correction, right? So basically making it even more accurate than the whole base pair specificity does, which is pretty neat. And then we will sum up that and then talk about some of the challenges in eukaryotes, right? So things are done a little bit differently, and having linear chromosomes might be a plus in one sense. Not sure what exactly, but maybe. But it causes other issues as well, right? And so we'll talk about that at the very end. And this actually is kind of fun because this is in many ways the reason why you get old, right? Which some of you haven't experienced yet, but you will. And we can actually talk about what that is at a molecular level, which is kind of neat. I like talking about that. Okay, so I hope this was useful, and I shall see you on Tuesday.